Hi, in this video, we want to take a look at multiple correspondence analysis. So we're in the situation where we have something that can be represented as a higher dimensional table, and we believe that we do not have independence with respect to each of the dimensions. So we want to dig in deeper. So just to back it up to, if I had simple correspondence analysis, then I have a 2x2 table, and not 2x2, a two-dimensional table, and rows and columns, and we will, and our evaluation, probably with a chi-square test, indicates that we do not have independence between rows and columns, and we want to dig in deeper. We now here, for multiple correspondence analysis, we're extending that to higher dimensional tables. Okay, all right, so the code in this example is modified from Modern Psychometrics with R by Mayer, and here's the GitHub source for the code. All right, so if you think about multiple dimensions of categorical data, well, I could represent that in a higher dimensional array using counts. And if you think about the numerical mathematics of it, things don't really work out the way that things do for like flat files and matrices and data frames. So what I have to do first, I have to figure out a way to convert the multi-dimensional table I have into a two-dimensional representation of the data. Also, so think about flat files in this way, and then we want to run the mathematics and understand what's going on. Okay, so after we get into a two-dimensional flat table aspect, there are two major options. One is eigenvalue decomposition of standardized residuals of the Burp matrix. Okay, the Burp matrix is going to be a two-dimensional count matrix that we'll use, or we can do singular value decomposition on the indicator matrix. The indicator matrix is a think of like dummy variables, that we use dummy variables to represent each of the levels. And so if I have, let's say, three categorical variables, what we do, we dummy variable each of those three columns, and with the zeros and ones, that would be our indicator matrix. We do multiplication of the indicator matrix with its transpose, and that'll actually give us the Burp matrix. So they're related, they're connected, there is a difference. So the Burp matrix is smaller and it's more compact, it gives the counts. The indicator matrix is basically full expanded version of the dummy variables that we've got. And in that case, we would be using singular value decomposition, because this probably will not be symmetric. So, sorry, would not be square. So the idea of eigenvalues wouldn't work out. Okay, so let's load some data. Let's go ahead and use the youth depression data set. That's in the MPsychoR package. Now, just to make it a little bit easier on us, we're just going to reduce it down to 3 columns. We're going to look at the question, I am bad all the time, I never have fun at school, and then we're going to include race. Okay, so I am bad all the time and I never have fun at school. These are coded as 0, 1, or 2, depending on the subject's responses. Now, the output gets kind of big, and the column names make things kind of wide later on in the example. So I went ahead and I reduced down the column names to make it a little bit easier to interpret what's going on. And I reduced down I truncated the race so that we have Asian Pacific, Black African American, Latino Hispanic, White Caucasian. Okay. So now the Burp matrix is a symmetric count matrix. It gives us a number of times that the pairs of categorical levels appears in our data set. Okay, so when we look through this, it's first I want to take a look at the output. So here, this tells me how many times C15 had level 0, how many times C15 had level 1, how many times C2 had level 2, how many times C21 was 0, how many times C21 was 1, how many times C21 was 2, And then these are the number of times that we have for each race. Okay, and so now when I look at a particular value, this is the number of times that Asian Pacific subject responded 0 to C15. Okay, so we're going off of rows and columns. Now you'll notice if I go down here, if I look at Asian Pacific C15, then I see the exact same value. All right. So it works out that since it's a count matrix, the entries are always greater than or equal to 0, and the every entry is less than or equal to the minimum of the value of the two diagonals that correspond to it. And we can see that this is a 10 by 10 table. All right, so how we proceed in doing our multiple correspondence analysis. So here, since we have a square matrix, we can do eigenvalue decomposition. Now, another option would be to take the C15, C21, and the race columns, convert each of the three to dummy variables, don't drop any levels, and do singular value decomposition on that matrix. Either way, we'll get results. They'll be pretty similar to each other. All right, so now let's actually execute multiple correspondence analysis. So we are going to do multiple joint correspondence analysis. We're going to use the correspondence analysis package, CA, and our method is going to be the Burp matrix. So this function, what it's going to do, it's going to compute the Burp matrix. Then it's going to take the first two eigenvalues from the Burp matrix, and it's going to take the first two eigenvectors, the corresponding eigenvectors, and then we're going to take a plot and look at what's going on. All right, so since this is a symmetric matrix, we know that it's going to be unitarily diagonalizable. We have a lot of nice properties whenever we have a symmetric matrix. All right, so now let's take a look at what happens. So really what we want to do, we want to look on the first dimension first, and we want to look at where things spread out. All right, so we can see race and white. And so I want to look horizontally. At this point, for the moment, I don't care about vertical position. So we have race, Asian Pacific, and then we see race, Latin, Hispanic, and we see race, Black, African American. So we can see Black, African American, and race, white, Caucasian are on, in opposite directions. When I look at, let's see, we have C21, C15, both are 0. So here, these are the cases where they don't have depression, or sorry, these questions don't indicate depression when they have a 0. And then I see 2 for both of these on opposite ends. So, and then we see the ones in the middle. All right, so that is consistent with that. So here, I'm interpreting this as a first dimension. It's kind of like an overall aspect of like a depression. So here, this is indicating to me that overall, we're seeing less depression among white Caucasians, Asian Pacific, and those who put in 0 for either of the 2 questions. Now, we're seeing more depression with subjects who put a stronger level of depression for their questions. Okay, and now let's look at the second dimension. All right, the second dimension, we see that we have 21.2, opposite 15.1. We see 15.2, 21.1, and then race Black African American, race Asian Pacific. Okay, so here I'm looking at this and I'm interpreting dimension 2 as picking up the difference between 1 on the 2-item questions and 2 on the 2-item questions. And then the rest I'm not going to really worry about with regard to dimension 2. So dimension 2 is kind of like distinguishing between different levels of depression indicators, while dimension 1 is kind of grabbing like an overall depression aspect. Now, configural frequency analysis, what happens here is, this is very similar to chi-square test, but we're looking at the residuals and we're looking at where do we have more than expected on our counts, where do we have less than expected on our counts. Okay, so let's go ahead and take the Harvard psychology data set. So here, this is taking psychology professors, taking their profiles from the websites, and then making a document term matrix off of the information after doing some text analytics to clean up the data. All right, so the Harvard Psych data set is a count matrix where the rows correspond to professors and the columns correspond to terms in their research profiles. All right, well, something about this is if we go through and look at the configural frequency analysis function, it wants to have 2 vectors, and it wants those vectors to be the levels and the counts in long format. Okay, so what we're going to do, I'm going to go ahead, I'm going to hit expand grid here, and then I'm going to grab the actual counts themselves. So here, this is the raw data from the document term matrix converted to a vector. So this will be a vector equal to the number of rows times the number of columns. And here, this is all the possible combinations of psychology professor and research term. All right, so now let's go ahead and run our configural frequency analysis. So here, this is a data frame of professors and the terms in the research profiles. Here's the counts, the number of times that each professor has that word in their profile. We're going to go ahead and choose to use binomial distribution or binomial test for this, and we'll sort on our number of observations. Okay, so now after I run this, all right, the CFA function spits out like a whole bunch of tests. It gives you a chi-square test, it gives you a z-test, it gives you a q statistic, and sometimes it gives you a binomial statistic. Okay, so that's a lot to like wade through. So what I'm going to do, I'm just going to grab the times that the binomial test is significant. This automatically does a correction for us, by the way, using Bonferroni, and I'm only going to grab the columns I'm interested in. So I'm talking about the label that we're interested in, number of times it's observed, what was expected, and then my test statistic. And now we're just going to look at the first 10 because there's a bunch of them. Okay, so we can see that this professor has memory far more frequently than expected, and Zoo has visual far more often than expected. And so we can see all of these, like we, Zoo also has human in here. So, this is kind of interesting. Memory and language is coming up, visual and human. And so we can be pretty confident that these are key aspects of their research. So if I was to go through and, I'm trying to target a Harvard psychology professor to maybe do research with, try to get them for some consulting, this would be an efficient way using web scraping for me to find the people I want to talk to. That way I don't waste my time reading a whole bunch of profiles on researchers who are doing things I'm not interested in. All right, so now let's kick it up a notch. Let's look at higher dimensional tables. So previously, that was a 2x2 table. It was a big table. It was still 2x2. Sorry, not 2 dimensions, not 2x2, 2 dimensions. Higher dimensional tables. Well, here, we have 3 variables going on. So what I'm going to do, I'm going to make a table. And then I'm going to convert that table to a data frame. All right, so what this does, this takes each of the dimensions of the table. So this will be a 3-dimensional table. What it's going to do, it's going to, the first dimension names, second dimension names, third dimension names, then the frequency. This will be a 4-column table. 3 like labels and 1 for counts. Now, once I have that, I can get my chi-square test. And so here I'm grabbing the label, the number of observations, the expected, the chi-square test statistic, and then the p-value. And so we can see that white Caucasians, in terms of not having depression responses, is far more frequent than we would expect based off of the independence hypothesis. And then Latino Hispanic subjects are putting in a higher level of depression responses than we would expect. Now, if we want to do a z-test, the z-test, so here we have going in both directions. So we can see that 1 and 0, which is on the lower aspect of depression responses, this is lower than would be expected. But the lowest response in terms of depression is much greater. And so we see higher for Latino, which we've already looked at. It's more frequent. And then let's see, once again, a higher depression response is more frequent with the Latino community than we would expect. All right. And so that is higher dimensional correspondence analysis. That's all I got for you. Take care and goodbye.